Last topic of the unit, last topic of the year. We call it the Doppler effect. We just watched a video from Big Bang Theory where Sheldon defined the Doppler effect as the apparent change in frequency of a wave due to the relative motion of the source and the observer. What do we mean by that? Well, by the apparent change in frequency, we're not talking about really changing the frequency. We know that once a wave has been made, the frequency of the wave stays the same. The wavelength can change, the speed can change, but once a wave has been produced, the frequency always remains the same. But sometimes it appears to change. So it's the apparent change in frequency of a wave due to the relative motion of the source and the observer. What do we mean by that? Well, either the source, either what's making the sound. The other video that we watched, it would be either the car horn or the fire engine siren, the source, and the observer would be the person on the side of the highway that was videoing the whole deal. The relative motion of the source and the observer. In both of the videos that I showed you with examples here, it was the source that was moving, the car horn that was moving. It was the fire engine that was moving. But it could be you that's moving. If a fire engine's on the side of the road and for whatever reason, the siren's on when it's on the side of the road, and you drive by it at a high speed, you're going to notice the Doppler effect as well. Not because it's moving, but because you're moving. It's due to the relative motion of the source and the observer, whichever one happens to be moving. Oh my goodness. We have, as our last equation for Physics 20, pretty ugly looking equation. FD is equal to VW over VW plus or minus VS times FS. First of all, let's identify what all those variables mean, and then we'll talk about the whole plus and minus and so on. FD is the Doppler frequency. This is going to be the apparent frequency. This is what we hear. I say that, but you know what? This applies to other situations as well. It's not just sound waves. The Doppler effect could occur with water waves. It can occur with light waves as well. You ever hear of the context of space in astronomy, red shifting or blue shift? A red shift or a blue shift? Yeah, some of you have, some of you haven't. That's the Doppler effect. Blue light has a higher frequency than red light. So if a planet or a star is moving towards you, the frequency of the light is going to appear to be higher, which means it's going to shift towards the blue. It's going to trick you into thinking this star is producing blue light. It's not. The actual frequency will be smaller than that. But as it's moving towards you, it appears to be a higher frequency, so it would be blue light. If it's going away from you, we get red shifting, because that means the frequency that you see is going to appear to be lower than it really is. And red light has a lower frequency than the other colors of light. Happens usually with sound, but it happens with visible light and other kinds of waves as well. The Doppler frequency, the apparent frequency of the sound or of the light or whatever wave it is that we're talking about. Fs, on the other hand, is the frequency of the source. Don't say frequency of the sound because it's not always sound. Frequency of the source. This is going to be the actual frequency. If the fire truck is sitting on the side of the highway and you're measuring the frequency of the siren from that fire truck when you're also standing on the side of the highway, that would be the actual frequency. The apparent frequency is what you hear when one of you is moving. Now this is where it starts getting really confusing. VW is the speed of the wave. Now usually that wave is sound, but not always. Speed of whatever wave it is that's causing the Doppler effect to occur. Whereas Vs, that's the speed of the source. A lot of people are going to get this mixed up. Vs sounds like it's the speed of sound, but it's not. The speed of sound, if we're dealing with the Doppler effect in the context of sound, would be Vw, the speed of the wave. Vs is the speed of the source, the speed of the car, the speed of the fire truck, speed of whatever it is it's moving. Finally, we have this whole plus minus thing in the middle. Sometimes the denominator here is VW plus Vs. Sometimes the denominator is VW minus Vs. We're going to take a second to think about the math involved here. And I want to see if anybody can figure out when it should be plus and when it should be minus. If the source is coming toward you, your Doppler frequency should be higher than your actual frequency, than the frequency of the source. So I'm going to say moving towards each other. I'm going to say FD is greater than FS. In other words, FD is a big number. And if FD is a big number, then the denominator there has to be a small number. VW and Vs on the bottom have to give me a small number to get a big number for FD. In order to get a small number on the bottom, then we're going to have to subtract. So it's going to be VW minus Vs as opposed to VW plus Vs. You may very well not remember when it's supposed to be plus and when it's supposed to be minus. Honestly, sometimes I don't remember when it's supposed to be plus, when it's supposed to be minus. It's just like that whole diffraction thing. Remember, the size of the opening affects the amount of diffraction, but also the frequency affects diffraction. And I told you guys that I never remember the frequency, how the frequency affects diffraction. I've got to think about that story that I told you guys about me listening to the radio at the bottom of the hill. That's how I figure out whether the diffraction is more or less given a higher or low frequency. Sometimes I got to do that here too. Sometimes I don't remember whether it's supposed to be plus or minus, so I figure it out. In order to get a bigger Doppler frequency, I have to have a smaller number on the bottom. In order to have a smaller number on the bottom, I have to subtract. Now, if the source is moving away from the observer, then FD is going to be smaller than FS. And if we get a small number for FD, then we have to have what kind of number on the bottom here? Small number right here, this number has to be big, larger, right? And if that number is going to be larger, then we're going to add them, VW plus Vs. Remember it or figure it out like we just did. Bottom line is, you got to be able to catch when it's plus, when it's minus. Otherwise, you're going to get the wrong answer. Take a look at an example. Page 432 here. It says, a train traveling at a speed of 30 meters per second. Its whistle generates a sound with a frequency of 224 hertz. You're standing beside the track as the train passes you with its whistle blown. What's the change in frequency that you detect if the speed of the sound in the air is 330 meters per second? We could make this a little bit harder by saying the temperature of the air is 20 degrees Celsius, right? Then you have to find the speed of sound and then do your thing. They give you the speed of sound here to make it a little bit easier. What do we got given to us here? Something is 30 meters per second. Something's 330 meters per second. Something's 224 hertz. Tell me what this is, this 30. V what? Is it VW or VS? VS, good. The speed of the source. Again, VS, we often think of that as the speed of sound. It's not. VS is the speed of the source. The train is the source, and it's moving at 30 meters per second. This one's going to be a V as well. This is going to be VW, right? The speed of the wave. In this case, the speed of sound, but it could be some other wave as well. 224 hertz. What is this? Its whistle generates a sound with a frequency of 224. All right, F. FD or FS? The Doppler frequency or FS? Good, FS, the frequency of the source. We want to find not the Doppler frequency, we want to find the change in the Doppler frequency, right? But let's do it twice. Let's say we want to find FD, the Doppler frequency, twice. And then we'll subtract them to get the difference in the sound. So let's solve for the frequency as it approaches. Or as it's coming towards me. I'm going to say FD is equal to VW over VW minus VS times FS. 330 divided by 330 minus 30 times 224. 330 minus 30 is 300. 330 divided by 300 is 1.1 times 224 is 246.4 246.4 hertz. So the actual frequency is 224, but it appears to be, as it's coming towards us, 246.4 hertz. Listen, we do this problem, we know that we chose this correctly, right? Whether it's supposed to be positive or negative. Because if we chose it wrong, then we would have got a number that was smaller than the actual frequency, which doesn't make sense, because we know when it's coming towards us, it's got to be bigger. So even if you do mess up and make it positive instead of negative, you should catch that. You should figure that out. Okay, now as it's going away from us, or as it recedes, we're going to say FD is equal to VW over VW plus VS times FS. It's going to be 300 over 330 plus 30 times 224. 300 over 360, we're getting 205.3 here. So we get two frequencies, one that's higher than the actual frequency, one that's lower than the actual frequency. If we want to find the frequency, the change in frequency that I detect, all I'm going to do is subtract those two. So now let's say 246.4 minus 205.3, and that's going to give me 41.1 hertz. Darren, give me the sound again. Give me the sound. All right, if we're good with that, let's take a peek at page 432 and take a look at the two questions on page 432.